Yeah, good morning, everybody. Welcome to this webinar on best practices for software development. And just to add names to the voices, which some of you have already heard. That is Kurt Stockbrough of Synopsys. And my name is Volker Eyert. I'm working for Materials Design. And we are both linked via the EMMC, the European Materials Modeling Council, and this webinar is part of the EMMC. It's organized by the EMMC, and it grew out of a white paper which Kurt and I have written recently, and we want to share the thoughts which we put down in this white paper with you, and hopefully have a vivid discussion at the end of this presentation. Okay. This should do it. So that's the agenda of today's webinar. I will give a short introduction of what we want to achieve with this webinar, and in the same sense, I will give you the scope of this webinar. Then we will run through different topics which we touched in the white paper and which we also want to discuss today, starting from model description and software architecture up to long-term support. And finally, we will give a conclusion. The webinar is organized in that way that I will provide the first part of this webinar of the time, and then Kurt will take over and run you through the rest of the webinar. Okay, what's actually the idea of the European Materials Modeling Council? We have become aware, and this is a well-known fact actually, that the academic development of methods, models, and software is usually quite strong. It's particularly strong in Europe, as we know. But when it comes to transforming that software into professional software products, then things become a bit weaker, and actually this becomes weaker and weaker when it comes to linking and coupling, and finally to the industrial exploitation. And the idea of the EMMC is to change that and to change actually the weight of the different parts in this game. This does not mean that we want to have less strength academic development, but we want to foster the other parts, and we want to foster actually professional software product development. We want to increase or improve the linking and coupling, which means making it the connection to the industrial exploitation. And in the industrial exploitation, there are several steps still to be done, still to be taken. Namely, we need translation. We need people actually who translate the methodology developments which have been taken in the last years, and to train industrial end users and to explain to them what could be done with these methods. And this includes actually consulting services, also contract research, for instance. It includes to prepare and to create professional software out of academic software. This also includes maintenance and long-term support, which are not actually in the intent of the academia. And so we thought that we take up these topics in the white paper, and actually provide with the white paper and with this webinar guidelines for academic development of software, because we became aware that there are some decisions in the development of software which are usually taken very early, but which may have long-term impact and also may have detrimental impact. And that's the point, that's something we want to avoid. Okay, let me tell you a bit more about the EMMC or the EMMC Coordination and Support Action, which was installed in 2016 by the European Commission. And as I mentioned, the idea is to foster materials research in the European industry. And since materials modeling is an integral part of materials research, this means that the EMMC wants to stimulate materials modeling as part of the industrial R&D, and to spread actually these news and to make people aware of the intimate connection of materials modeling and materials research. And in doing so, what we want to do is we want to combine the expertise of academic and industrial partners, and we want to strengthen the links between the different team players, namely the software developers, which are mainly academic, the distributors, and the end users, which are mainly industrial. So that's actually what we want to do, and that's the goal of the EMMC. And the white paper in particular, as I mentioned before, as I indicated before, wants to provide academic researchers with guidelines for this sustainable modeling software development. And as I also mentioned before, we want to increase the awareness of the importance of early design decisions, because if wrong decisions are taken, as I mentioned, this may have long-term negative impact. And finally, there are some best practices to be shared for software development. That does not mean that we want to tell academic developers how to develop software. This is not what we want to do, but we want to just close the link between the different partners and just start a discussion about certain topics. Okay. Let's move on. And as you all know, or most of you may know, there are huge amounts of scientific software developed over decades. And some of this software, or most of this software, is not really used in a professional way. This has several reasons. First, mainly in academia, mainly students and postdocs develop this software, and usually they have a very short time horizon. They just want to finish their thesis, and then usually they leave after that. And so this leads to a particular way of coding, which is usually called quick and dirty. And people just want to get some results out of their software, and they don't care about how the software is written, how clean it is written, how well documented it is. And so this is a very short time horizon, which is understandable, but it's not good for long-term development of software. And in addition, in academia, usually there is put less emphasis on intellectual property and licensing considerations, which are, however, very important and should be taken into account from the very beginning. Okay, on the other hand, we see an increasing degree of commercialization. In particular, this is well known for quantum chemistry codes. The chemical and pharmaceutical industry is using quantum chemistry codes for a long time, for several decades, and has usually a quite good experience with that. And in the materials science part, companies like Biovia, Materials Design, and Schrödinger Quantum Wire Synopsys, SCM, have established in the last, let's say, 2 decades, maybe a bit more, and they have established a value-added chain from academic research to industrial deployment. But still, there's much room for improving this value-added chain and to include actually the relationship between the different, to improve the relationship between the different partners. And for this reason, the software development guidelines have the goal of a more rapid integration of the academic software with industrial software. Okay, let me start then with the topics which I noted in the agenda, which we want to work through step by step. So, of course, this is just project management. It is very important to do an early planning and to be aware of the scope of the software, of the goals you want to achieve with the software, the ways you want to use the software. So this is for the present day, but of course you should also have a vision for the future developments, because this has a strong impact on the software architecture. For instance, you may want to modularize the software and to define define interfaces between the different modules. And this, of course, serves the purpose that later on you can quickly change the software and improve it and include new modules, etc., etc. Some other advices are to use libraries whenever possible. So there are standard libraries. One should not try to reinvent the wheel, but use these libraries whenever possible. One well-known example is LAPACK, and there are other libraries, of course, on the market. And in addition, what you also may want to do is to try to combine selected software modules into a library that can be shared and maintained by several groups. And an example for that is, for instance, libxc, which is a standard library for exchange correlation functionals. Okay, so these are early decisions which you want to take. Another early decision is referring to the programming language and the deployment. So as you well know, there are in scientific computing, there are several most used programming languages, namely Fortran and C++ and Python. The difference is that Fortran and C++ are compiled languages, and they offer a degree of object orientation. In Fortran, which has a very long history, this has not been always the case, but with the modern Fortran implementations, you can do object-oriented programming. And this allows you to move away from the old so-called spaghetti codes, which were sometimes written in a very crude way and in many cases were not really understandable for other developers. So the usual way, especially in academia, was just to throw away such an old code and to write a new code. And so this, of course, increased the amount of code which was created, and this didn't really improve the situation. Okay, both languages, Fortran and C++, have a good performance, and there are many compilers available for both languages, free compilers, commercial compilers, and there are also many libraries available for these languages. Okay, as I mentioned before, Python stands a bit out because it's not a compiled language, but it's an interpreter, which allows for fast prototyping. It is a bit less performant, but it can be combined, it can be interfaced with the compiled languages at increased complexity. A slight disadvantage is that because it's an interpreter, errors can be found only at runtime, and this may be, in some cases, maybe a bit complex. Okay, there are other aspects. Namely, on the long run, if you have created a software, you want to run it in parallel. So there are different ways for parallel programming. And you also want to use GPUs. There are also different software packages, well-known software packages for GPU programming. So this has become kind of a standard these days, but you may take that into consideration from the very beginning. Okay, there are some two more, let's say, hot topics which we want to put some emphasis on, and these are coding guidelines and source code documentation. Coding guidelines are especially important if you work in a team, because other people, other team members may work or start from code you have created, and for that reason they need, or everybody in the team needs to use the standards and to be consistent with the standards used by the team. And these guidelines, of course, increase readability and improve the working in the development team. So that's very important, to stick to certain guidelines which have been decided at the very beginning. Simplest way is just how much you indent lines in a code, or when you start a loop, or things like that. So this sounds very trivial, and it actually is, but you have to agree on that in a team, and that makes life much easier for everybody. The same, of course, holds for source code documentation, which is very important in a development team. There are automatic tools like Doxygen or Sphinx which can be used, but source code documentation is not only important for development teams, but also for single developers, because usually once you have developed a piece of code or written a piece of code, if you look at that back after half a year, you may still have, or you may have real problems understanding what you have done half a year before. So documentation is very important. However, it needs a bit of self-discipline, but it's really worth the effort. Okay, let's come to a very important topic, namely intellectual property and license considerations. Of course, scientists and people from academia, they are not really excited about legal matters, but still they are very important. And this is due to the fact that decisions at an early stage are of crucial importance, and this is even more so when many people are involved. And this is for the following reason. As I mentioned before, in academia, people usually have a very short time horizon. They work on a project, they develop software, and then they leave after 2 years, 3 years, whatever. And usually it's very hard to get hold of these people later on. But everybody who writes a code has the copyright on this code, and you cannot change the license of a code, especially if it's developed in a big team. You cannot change the license without asking everybody in the team, everybody who has worked on that software. So changing the license model later on, after some people have left the team, can be a very difficult task. And for that reason, it is very, very important to take the main license decisions and copyright decisions from the very beginning. Of course, this touches questions like the ownership and the intellectual property rights, which of course depend on national laws, international regulations, but still everybody who writes a code has a copyright of the code and has to be asked whenever the license model is changed later on. Okay, there are different license models, and one has to make an early decision on that. The license may be permissive, copyleft, or proprietary. Let me explain that in a few words. Most of us have heard something about all these different terms, but it's very important to have a more and more clear understanding of that. So permissive licenses are usually the free and open software licenses. However, you have to distinguish between free and open source. The software can be open source, but it does not necessarily have to be free. What does free software mean? Let's look at the definition by the Free Software Foundation, which is very old, actually. And they defined 4 different freedoms, namely the freedom to run the program for any purpose, the freedom to study how the program works and change it to make it do what you wish, the freedom to redistribute and make copies so you can help your neighbor, and the freedom to improve the program and release your improvements to the public so that everybody can benefit from the improvements. And of course, this needs open source software, because otherwise you cannot improve the software or study how the program works to some extent. But as I mentioned before, open source software does not necessarily mean that it's free. There are other definitions of open source software, which are based, for instance, on the Debian free software guidelines, and these are largely equivalent. And then there are yet other free licenses, permissive licenses, actually the BSD license, the MIT, Apache, and the Educational Community license. Okay, I mentioned 2 other types of licenses. Another type is the copyleft license. This applies to free and open software, and modified versions must preserve the freedom 0 to 3, which I mentioned before. And for that reason, these licenses are also called viral licenses, because once you open the Pandora's box, or can actually, you cannot close it anymore for that particular software. Examples are the GPL, the LGPL, and the MPL, which are well known and are found in the internet. And finally, we have proprietary licenses, which include constraints. So maybe that the source code is not available, there's a license fee, and they usually come with commercially developed software. And what should also be mentioned, they come together with long-term support, which is usually not provided or cannot be provided by academic institutions which have the aforementioned shorter time horizon. Okay. If you deal with software licenses, you always have to take care or think about backwards and forward compatibility. In this graph, you can see the different license types, namely permissive, copyleft, and proprietary. And if you have a permissive license, you can apply that to a code which has originally or which has before been permissive. And once you have a code with a permissive license, this can be changed into permissive license, copyleft license, or proprietary license. There are even software packages which are distributed under different licenses, for instance, a permissive license for academic use and proprietary license for industrial use. This can be applied to the same software actually. If you have a copyleft license, if you go backward, then of course this can be created from a permissive, from a software under permissive license or copyleft license. And of course, once a software is copyleft licensed, then it has to stay that way. That's what I termed the virality before. And finally, if you want to make a software proprietary, this can only be done if you have a software which was always proprietary, or for a software which has been permissive before. Okay, the first step actually you want to take as a programmer, if you want to deal or if you want to have into intellectual property issues, is just to add to each part of your software a copyright notice. And this can be easily done. There's an example given here. You just add to each file which you have created, to each source code file, you add just the version and the name of the code and the date, for instance, and your name, and you add a copyright notice. which means that the code is copyrighted by you. And then you can refer to a special copyright file, which you distribute along with the source code files, or alternatively, you can just refer to the GPL or LGPL license. Then you don't need your own copyright file. But be careful with GPL or LGPL licenses because of the virality of these licenses. You can always change to a copyleft license later on, but be careful at the very beginning. Okay, and as I mentioned, you can refer to these licenses right away, or you can include them in your these GPL or LGPL in your distribution, or alternatively include the BSD or MIT license or whatever. Okay, let me stop here and hand over to Kurt, who will guide you through the rest of this webinar. And Kurt, the floor is yours.
Thank you, Volker. So I will just grab the ball.
You take it, okay?
Yeah. Okay.
Good.
So you should be able to see my screen now. So
yes,
yeah. So this is okay. So yeah, here's Kurt Stockbrough from QuantumWise Synopsys. So I'll take the other part here. So let me just put my let's put it in presentation mode. Okay, so the next topic is testing. So testing is a very integral part of software development. So yeah, let me just testing is a very integral part of software development. Actually, at Synopsys, we do test-driven development. So before we write any code, we write the test, and then afterwards we write the code that is then automatically tested. It's very important if you distribute your software on different platforms, because we very often experience that once you implement on one platform, it doesn't necessarily work on another platform due to compiler issues. So it also ensures consistency of results obtained with different releases, and also if whenever we experience a bug, we make a new test such that we are sure that this bug will never appear again. So there's a test checking for this bug, and then you should run your test very often to ensure the consistency of the software. In our case, we run it every night. And you can have different hierarchies of tests. You can have small tests that you run very frequently every time you do a new commit, and others very long tests that you do before a release. So once you have implemented a new functionality in your software, you should verify that it's actually doing what it's supposed to do. So in this case, it can be good to make a quick, have done a quick prototype that is maybe not so efficient, but it's more simplistic, so you can check against that. Else, if there are other implementations in the community, you can check against other implementations of this functionality. The next step is to make sure that it's actually what you are simulating has a value. So so you need to validate it against the experimental data to make sure that it's actually simulating nature. And typically, such a validation study is then also published in a scientific paper. one often see that new softwares are only applied to very simplistic systems, and then it's released, and then the users take it to all kind of complex systems. So it's good to test your software also not only on the most simple system, but think about what are the complexities that can be applied, and make sure that it also works for very complex systems. Then how do you organize the software development? If you're sitting alone, it's of course very simple. But in fact, also if you are a group of one person, it still can make sense to use some software development models. Today, the most popular models are agile software development models. So what we are using here at QuantumWise is the Scrum model. This is also what Google or Apple or other big companies are using these days. And the aim here is to put your development into small cycles that are more easy to get an overview of, and that you can see progress all the time, even when you are looking at working at a big feature. So in the Scrum model, you work in a small team, typically between 3 and 7 people. So this is the Scrum team sizes we have here at QuantumWise, and we typically work in 3-week cycles. So the first part is to plan how much work can be done in the next 3 weeks. And in our case, all tasks are made into all what we call the user stories, are made into smaller tasks of 3 to 4 days length. And then all the tasks are put on what we call a Scrum Board. So this is what you can see in this picture here. And then in the beginning of the 3-week sprint, then all these post-it are on the top of the Scrum Board. And then the developers in the team checks out a task so that it goes to the next level. And then they will work on it. And when they're finished, they will put it to the next slot. So that's in review, and then another developer will look through the developed source code to check if it is in accordance with the coding guidelines and if it's working and so on. And once the review is done, the task goes to the bottom. So, and this happens during the 3 weeks sprint, and every morning the Scrum team meets and tells what have they worked on yesterday, what will they work on today, and do they need any help on some of the issues they're working on. After the 3-week sprint, there's a demo where each developer will present for the rest of the organization what have been developed during this 3 weeks. In QuantumWise, it's done through a small 1 to 2 minutes video of the new feature, and then the sprint ends with a retrospective where the developers discuss how the work was performed and if some parts of the work process can be optimized. So in this way, Scrum is not a static thing. It evolves all the time, and the developers work on making it more and more efficient. So it's a very efficient way to make software, and since it's in 3-week cycles, the developers do not get stressed. Another important aspect of software development is version control. I remember my first software there, we were just sending around binaries in many different versions, and now zipped directories with many different versions, and in the end you completely lose control, and then one version is not working and you cannot figure out what went wrong. And today you have advanced version control system that can control all changes, and you can go back to different versions to make sure if there is a bug that you have a version, you can see at which version this bug was introduced. There are different version control systems. The most popular these days is Git, and this is also what we are using, and this allows the developers to work on many different branches. So often we work at maybe 15, 20 different branches at the same time, and the Git allows you to easily merge these different branches into the main branch. So here it's also very important to have good testing systems to make sure that once a branch is merged into the main branch, all the functionality in the main branch is still working. So I can only stress how important good testing systems are, and actually we have more testing code than actually actual source code. So if you want to go to professional standards with your software, you need a very big testing system, and in the end it pays off. Another aspect is metadata. So this is more related to once you have a software and the user is running it, that they can afterwards see when they go back to old data, which version was it run with, what was the release, which release was it, such that they can reproduce old data, and if something went wrong, it's possible to find out exactly which version has the problem. Then it's documentation. So we actually went a little through that before. So on the source code documentation, you also need user documentation, and actually which things it's possible to, if you use Python, to put in your also user documentation in your source code. So this is what we are doing. So in this way, you don't need to maintain two different sources of documentation. So you should try to automate documentation and make the maintenance as simple as possible. Once you have many different sources of documentation, it's difficult to keep it up to date. Another very simple thing to do, and also it's very popular, is instead of having written documentation, you can do small video tutorials of different features, and often for users it's easier to understand how to use a software from viewing a video, and maybe it's also more fun than reading lots of documentation. And of course, as a commercial company, we are very aware of marketing. So if nobody knows about your product, nobody will use it. So that's also important. I think for scientific software, it's often enough to make a good scientific paper and participate in conferences, and in this way raise interest in the software. So the kind of different parts of good user documentation is, first of all, you need an installation guide. If people cannot install the software, they never get started. Once it's installed, you need a few workable examples and some case studies, and then for people to after that go on with their own examples. They need documentation in terms of what are the input variables, what are the output files, if there's a graphical user interface, how it's used, and they also need some background information on what's inside the software. However, often this background information can be in the form of a published paper, and there are many journals that like to publish papers giving backgrounds about different softwares. Support, I mean, if your software project becomes popular, you can be sure that people will need support, and they will ask you a lot of questions. And actually, sometimes I've seen several scientific projects where the developers, they just get unproductive because they get so many questions that they need to answer. Not all questions are by users with insights. So yeah, so you can spend a lot of time on this. So you need a plan for how to handle that. I mean, one way is to work with a commercial company that commercializes the software and then takes care of the support. We see that's the case of many softwares like RASP or CASTIP. Volker and I have written this paper as part of the EMMC, and this webinar was to kind of go through quickly the points in the white paper. It's also the idea to get some feedback from the participants. I mean, on the topics, whatever we are missing, some important topics, whatever you agree on the points we have done, or if some should be built out, and we will then make a version 2 of the white paper, including these points that we get from this webinar, or maybe you can email us afterwards. So, but just to summarize the content of the white paper and this webinar, before just starting on a new software project, it is important to spend a little time and think about some early design decisions that will, if it becomes a successful project in the end, you'll be very happy that you spent this time in the beginning. So the topics are this: what is the scope of the software? Think about some vision of where will it go in the future. What are the models? How can that be put into a good software architecture, and which programming language should I use? Then you need to organize the software development process, in particular if it involves several groups. You need to consider which license model should we use. You need to use version control and have source code integrated in as an integral part of the development. You also need to think a lot about testing, so that needs to be an integral part of your development process, and you need to verify and validate the final software. And finally, once you have a product, it needs to have user documentation and support for it to be valuable to anybody else from your own group. Okay, thank you. So this was all from now. So now we would like to have a Q&A session, and you can post questions via the GoToWebinar. So let me see. Okay, so I think there's a poll now, so I will just launch that while we are waiting. So, and please feel free to also put on a question. So I think we will close the poll now, and then I will start the Q&A session. So okay, so okay, so there's question here from Al so there's a question here: what is the process of writing testing code? Is there best practice for this? There are different online libraries that will help you to write testing code. So basically what you have is two types of tests. There are unit testing. So this is where you test a function. So then the test code will go in and call a function, and then it will check what is the function. It will call the function with different input parameters, and there you should make sure that you cover all the different use cases of this function, and then the function will return an output, and then you have to check that it returns the expected output. So for instance, if you have a Poisson solver, then you call it with some input density, and then you check that your Poisson potential gives the expected result within a certain accuracy. So then so maybe we can supply some links to different resources of testing environments. So you will need different testing environments, whatever you use, Fortran, C++, or Python. So this is for unit testing. So there you need to use some testing environment. Then the other part is functional tests. There, in fact, I mean, there are also testing environments, but you can also just have your own scripts. So a functional test is that you run the final software with some input, and then you check what is the output. So there you can have a number of input files and different type of calculations, and you check that the code consistently keeps the same. So I think this is what most people use, but this unit testing is very important also to because it's much faster to run the unit test, and this is something that you can use for continuous testing. So I will go to the next thing, that is, what do you think about making a Python C++ interfacing? This is what we are using at actually QuantumWise. So we develop all functionality first in Python, and then if some of the parts of the code is too slow, then we move it into C++. And in our case, maybe 80% of our source code is in Python, and then 20% is in C++. And there are automatic ways of making Python bindings to C++ code. So it requires some computer science skills to do it, but it's a very flexible way of programming. Okay, maybe here's one. Maybe you would like to answer this, Volker. So the next question is, can you talk about the development guidelines when integrating the software with existing third-party industry standard software through APIs?
Yeah, I can do so. Well, I mean, just take a very simple example. I mean, if you have libraries like LAPACK or so, I mean, you just have to obey the calling sequences, and then you call these libraries. I think that's more or less straightforward. Maybe I'm overlooking something here. Do you have some more comments on that, Kurt?
No, I mean, so of course, often these, for instance, if it's linear algebra libraries, maybe they have a certain structure of the data layout that you need to follow. So, but you can embed that in, if you use C++, then you can embed the library calls inside your classes. So that's typically what we do at QuantumWise. Then we have, for instance, a matrix, our own matrix library, but it makes calls into LAPACK or the Intel linear algebra libraries. We can set up different libraries, but there's a uniform interface from our side, so it's embedded within the C++ source code. The transfer of our data structure to the library data structure. So I think, I think that's can be recommended to have some kind of internal interface that will allow you also more easily to switch to new libraries, because then it's only within your own your object code that you need to change it, and the rest of the code still have a uniform interface.
Let me just add a word of caution. You should also take care of the version of the libraries. For instance, with LAPACK, the older versions are not thread safe. So if you do parallel programming, you may have strange encounters with the older versions of LAPACK. And so take care that you always use the latest versions of libraries. In addition, Laidback in particular, or some other libraries also, offer the nice feature that they also distribute the source code of the library. So if you want to distribute your code, you may also want to include the source code. So this is an additional way of, or this allows for an additional way of compiling the code, namely with the linked library as it is, or with the source code of the library compiled by yourself. This may be in some cases useful if you want to do, if you want to trace backs, or if you want to have a look at the closer look at the interfaces and things like that. So that may be an aspect worth thinking about. Okay, shall we move on?
Yeah. So there's one asking me about Git capabilities. So yeah, I think, I mean, I'm not a sufficient expert to kind of answer that, but I can just say I think Git is what's used by most kind of advanced groups these days, and it has a lot of capabilities. So one nice thing is that all developers have the full repository on their laptop. So in that sense, if one of the machines crashes, all the other ones do, or if the main if the main repository crashes, then there are also local copies, and you can do and you can work just on your local copy, and then and you can commit on your local copy, so you're not reliable on an internet connection. And once you have an internet connection, then you can kind of upload it to the main repository and make sure you are in sync with the main repository. And it's very good at merging. So I think it's a little complex. It takes some time to learn Git, but I would, I mean, I think Git is the kind of best, at least this is what I hear, is the best version control system these days.
Yeah.
Then there's some about these different testing systems. I mean, I can not comment on that, so I am not expert in these different testing systems. So here's mentioned Travis, Jenkins, GitLab, CI. So maybe what we can try to do is to find some links to different resources on the net on different testing systems. It's I can only say you need to pay attention to this, and in the long run, you'll save a lot of time by having good testing systems. And the earlier you start, the easier it is to maintain. I mean, once you have, as we have here, 2-3 million lines of code, then starting testing that, I mean, then you will have 20 people working for 2 years. I mean, and it's will never get done. So start early on this and take the time to find out how to implement a good testing system with unit tests.
Yeah, and as you mentioned before, I mean, you have to assure that you have upward compatibility. So whenever you create a new version of the code or you change the code, you want to test that it's upward compatible. Right.
Yeah, exactly.
Okay, yeah.
Then the next question is, most academics who write code are not trained in software development and as such have got no clue on how to plan the work. Does there exist some open software that helps you to structure the code and work? So here at QuantumWise, we use a target process. This is a very advanced system for planning your work, but that's not free, so you have to pay for it, and probably it's too involved. Earlier we used Boxilla, but that's for bug tracking. So I know there are, and I think Boxilla is free. I will check maybe if there are some open source free systems also. Okay. So then there's, do you think that Fortran coding can still be considered a viable option for industrial code development, or would you just rewrite your old code in a more modern language? Yeah, that's a good question. I mean, I think there's a lot of industrial Fortran code. I mean, it's simply as a company rewriting a few million lines of code. I mean, that's a huge investment. So whatever. So I think I mean, Fortran code that have been running for many years also have been kind of verified and validated over a long time. If we take in our fields like Gaussian, that's a Fortran code, and it has existed for so many years, and I guess it's still the industrial standard for quantum chemistry calculations. I guess nobody would start rewriting that in C++. So I don't think it's a must to rewrite your old code. But if I should start a new code project, probably I would not choose Fortran. On the other hand, you need to look at who are the contributors that you expect to have. If your contributors do not know anything else than Fortran, it might be difficult. Another aspect I think should also be taken into account is, are you going to use master students, PhD students? Maybe they should be trained in more modern languages that are used outside the kind of physics community. This will increase their job opportunities. So that's an aspect that we didn't put so much into this presentation, but which I believe is important, that actually the most important obligation of universities is to educate students. So you should think about the tools you introduce them to. Can they actually use that in other fields also afterwards?
I wouldn't also call. Sorry, go ahead.
Yeah. So if this is as part of the training of, or if you're going to use master students and PhD students, then think about using more professional software tools as used in the software industry.
I wouldn't necessarily call Fortran a not modern language. I mean, there are even people who say that modern Fortran is even more modern than C++. I don't want to enter discussion like that. And Kurt also mentioned other aspects like job search later on, and so on and so on. But I think the bad image of Fortran nowadays is mainly due to the long history of this language. People are usually connecting the name Fortran with the old versions, say the versions of the 60s and 70s, where you could really create a lot of spaghetti code. But since then, the language has drastically evolved, and it is nowadays, it is really a modern language which offers all the concepts which you also have in C++, and it can be very efficient. So it's mainly, in my opinion, it's a decision of personal preference rather than a decision between old and modern. It's really more like that, and you should really make your own choice and make your own preference. And of course, it depends on the style you write your own code. I mean, you can write bad code in both languages, in C++ and in Fortran, and you can write good code in both languages. And you should also consider that once you start with a language, you build up a lot of experience in problem solving and mathematical tools, algorithmic tools, and so on, which you would not simply throw away. It's really worth thinking about which language you would prefer, which language you would like to use.
Okay, so maybe I will just close the session now with the last question, that is, where can the white paper be found? So that's on the EMMC website, but I think we will send out a mail to all the participants with a link to the white paper. Okay, so thanks everybody for attending the webinar.
Yeah, also many thanks from my side, and thank you for participating in the poll. And yeah, thank you and have a nice day.